Hi, class. So this section, we're going to go over two-way ANOVA, and we're just going to, there's two kind of objectives that I have for you, and that is that you understand what the interaction between two factors is, and you can identify if there is interaction going on. And also, I want you to just be able to read the output of a two-way ANOVA test and come to correct conclusions. So let's share my screen. So this is two-way ANOVA. And like I said, we want to analyze a two-way ANOVA design and understand how this is set up. And we want to, I want you to more just understand an interaction plot that we're going to talk about, and then perform two keys test. So there, in one-way ANOVA, there's one factor that we're interested in. And remember, in an experiment, there might be one factor that affects a response variable. So, for example, how much weight you lose. One factor could be a weight loss pill that you're taking. That could be a factor in how much weight you lose. But also, how much that you're exercising might also affect that, how much weight you lose, right? And of course, we know that it does. So when we have two factors like that, sometimes we want to do an experiment and we want to include both factors and the results from both factors in one test, and that's two-way ANOVA. And I feel like it's valuable because this two-way ANOVA test will tell us if there's two things that are interacting. Like two different medications could actually interact with each other, and maybe medicine A by itself might work wonderfully. Medicine B by itself might work great. But when you put them together, they might both cancel each other out and might be a horrible combination. So there might be some interaction effects going on. And so the two-way ANOVA will catch stuff like that. So let's, so sometimes in experiments, we control the factors by fixing them at a single level or by fixing them at different levels, like giving you either 5 milligrams of the drug, 10 milligrams of the drug, or a placebo, right? We fix them at different levels, or we randomize so that their effect on the response variable is minimized. So in previous sections of one-way ANOVA, we were really only interested in one factor, maybe how this pill is affecting your weight gain, right? Now we're going to look at two different things that might affect your weight gain, like I said. So in two-way ANOVA design, they design it in a matrix kind of like this. It looks like a table, and they match every single factor with of A with every factor of B. So here, factor A is male or female, and factor B is either a placebo or 5 milligrams of this medicine. And in this example, they're trying to figure out the hemoglobin of males. And of male and females, just of people. So they have, some men are taking the placebo, some women are taking the placebo, and some men are taking the 5 milligrams, and then some women are taking the 5 milligrams. So every level of the medication is matched with every gender. Well, there's only two genders, but the two genders. And if we had more, if more levels of factor A, then they would be matched with both levels or multiple levels of factor B as well. A is usually they like to talk about factor A being the rows, just discussed in the rows, and then B is the columns. So this is an example of a 2x3 factorial design. They say a high density lipoprotein, HDL cholesterol, is a good cholesterol because it helps to reduce the amount of bad cholesterol in your system. A pharmaceutical company developed a drug that is meant to increase HDL levels in patients. They obtained volunteers whose HDL cholesterol levels was roughly the same and randomly assigned them to 3 groups. Group 1 was a placebo group. Group 2 was a 5 milligrams of the drug, and group 3 was 10 milligrams of the drug. In addition to the drug doses, the researchers considered age to be a factor in the analysis. So they divided patients into the 18 to 39-year-old category and 40 and older category. And the design is down below. So it's almost like they do like 2 mini separate experiments. They do like the experiment for between 18 and 39-year-olds, but for all 3 levels of the drug. And then they kind of do a separate experiment on the left or whatever of 40 years old or either and older, and they do all 3 levels of the drug as well, right? And they have it all summed up in this table. And you're like, why don't we just do 2 separate experiments and 2 separate things here? And then we'll just do one-way ANOVA, right? But with 2-way ANOVA, like I said, they're gonna give us information about something called interaction between the 2 variables, which is valuable for us. So so they say that kind of table, they call that the 2 factors were crossed. Every level of factor A has people who are going to be, who has data collected from every level of factor B. And if we kind of were to ignore, now how are we going to like interpret these results? So if we kind of ignored like factor B and just focus on like factor A and like looked at how the response variable is changing from a low level of A to a high level of A, we call that the main effects of A. And if we ignore factor B or more factor A, sorry, and we just look at between the low and high levels of factor B, then those are the main effects of factor B. And if changes, if the effects of let's say factor A change at different levels of factor B, then we would say there's interaction going on, right? If there's no interaction, if B just is not affecting A at all, then at every level of factor B, the response variable would react the same way as we go from low to A, high to low in factor A for every level of B. However, if B is really affecting A, then higher levels of B will be different than lower levels of B. The effects of A will be different for different levels of B. So let's see an example. And here's an example of interaction. So they're just saying sleeping pills and alcohol, both of them are fine just by themselves, but then they can be fatal when you're taken together. So that's interesting. Okay, so let's look at the main effects and the interaction effects. Suppose we have 2 factors, A and B, and each factor is fixed at 2 levels, high and low. The value of the response variable at each level is represented. For example, the response variables when both factors A and B are set to low are 3 and 5. Okay. The main effects from A is basically like if we ignore factor B. So like if factor B is not even there, right? So we don't care about this line being there anymore. And we don't even care about that. Like, we're just going from a low, or like actually we're comparing the high level of A, the response variable when we have a high level of A, and comparing it to the mean of the low level of A, right? And so that's what they do. They take 8, 4, 17, and 18. So all those 4, they take the mean of that, so divide by 4, the number of numbers there, and they find the average response variable for a high level of A. Then they look at the average value the response variable for a low value of A, so the 5, 3, 6, and 8. They divide by 4 and find an average, and they call this the main effects of A, because this is like, if we ignore B completely, then, and we look at what the response variable for a high level of A compared to the response variable for a low level of A, then we subtract those, the average for high level of A minus the average for the low level of A, and this is 6.25 units. So it means that increasing factor A on average will increase the response variable by 6.25 units. So that's good. But I mean, I guess if we want a higher number in response variables, then maybe this is good. That apparently applying whatever treatment A is probably good. All right, and then let's look at the effects of B. So the effects of B are main effects, we call them main effects of B, are if I ignore A like it's not there, and we just are focused on the low level of B. So like if A is not here, then we don't care about low and high, and we don't care about this line being there at all, right? And we just look at the low of B and compare it to the high of B. And so they did the 6 plus the 8, or the 8 plus the 6 plus the 17 plus the 18. So that's right here, divided by 4. So they find the mean of the high level of B. And they subtract the mean of the low level of B. And they subtract those, and they say on average, increasing factor B causes an increase in a response variable of 7.25 units. Okay, so those are the main effects of A and B. All right, so let's go to the next screen. And now we're going to talk about the interaction effect. So now we fix just low level of B. We just look at a low level of B, and we see what happens to A at a low level of B, right? So let me copy this back over really quickly. Let me see if I can get just this little table for us so we can see it over here on the other screen. Okay, that's perfect. So for a second, they're like, I want to see what happens to factor A if we ignore the high level of B for a second, and we're just focused on what happens to factor A as we go from high to low if there was no high factor of B, right? And so they do 8 plus 4, and they find the average of that. And then they find 3 plus 5, they find the average of that. So, and they find that, so they say this, so this means that the effects of A at a low level of B are 2 units. So when when we are at a low level of B, we would expect the response error variable only to go up 2 units when we increase A from low to high, which is troubling because a minute ago, we thought on average going from low to high on A would give us 6.25 units, right? Let's go run screen back here. Right, the main effects of A said 6.25 units. So we thought that, hey, when we increase A, that the response variable should go up 6.25 units. And if we look at just the low level of B alone, there was and increase just A, then it only goes up 2 units, which is a lot smaller than 6. I mean, that's a third of the amount that it's going to go up, right? So already I'm thinking there's some interaction going on here, like, but let's look at even further. So now they look at just the high level, of B. So they ignore the low level of B and they focus on the high level. And they're like, okay, well, what if we are applying lots of factor B? Let's see what happens to A. Let's see what the effects of A are. So they find the 18 plus 7, find the average of that, and then find the average of 6 plus 8. That's what they're doing here. And they subtract it, and the effects of A at a high level of B are 10.5 units. So that means that really, to me, when we had a low level of B, factor A was not really working. It only went up by 2 units. But when we are at a high level of B, then A does really work because the difference between A high and A low is really big when we're at a high level of B. So to me, A is only working if B is at a high level. And so that means we have interaction going on between these two variables. If there was no interaction, then you would expect this to be close to 6.25, and which was, the average increase in the response variable over all of the main effects of A. And but they're not close to 6.25. They're not anywhere close to 6.25. So they're definitely showing to me that like I said, there's interaction going on here. So let's go on and just so that you know, if there's interaction going on, we don't want to just jump to conclusions and say, well, medicine A works, because obviously there's more going on here. A only works when B works, is a high level, right? So we just have to be careful when we have to be extremely cautious if there is interaction going on between two variables. And looking at the main effects can sometimes, if you're just focused on the main effects only, it would cause you to come to wrong conclusions, right? So let's look at the next slide here. So let's see an example. We're going to see a full 2A Anova test and how to actually look at the results. Suppose the rice farmer is interested in comparing the fruiting period for not only the 4 fertilizing types, but for 2 different seed types as well. The farmer divides his plot into 16 identical subplots. He randomly assigns each seed and fertilizer combination to 2 of the subplots and obtains fruiting periods shown on the following slide. Identify the main effects. What does it mean for the 2 to say that there is an interaction between the 2 factors? What does it mean? Okay. And so here's the data. And they just go into more detail here, that the main effect of A is the change of the response variable, which is the fruiting period, that results from changing the different fertilizer type, because that was factor A. And then factor B is the change in fruiting period, which is the response variable, as a result of changing this type of seed type. Those are the main effects of A and B. And if there's an interaction, that means that maybe the seed type works for a certain only one of those fertilizers, and not other fertilizers, or but yeah, if the fruiting period there is changing with seed type, then we'd say there's interaction between those two. Okay, so here is the things for a two-way analysis of variance test. The populations from which the samples are drawn must be normal. The samples are independent. The populations have the same variance. This is this is to verify the small. So this is the same as one-way ANOVA. The largest sample standard deviation is no more than twice the smallest. And there's actually 3 separate hypotheses that we're going to be, and so 3 p-values that we're going to be checking for two-way ANOVA. The first one is any interaction, because if there's any interaction, we probably won't, like I said, we're not going to be interpreting the main effects or with extreme caution. So so the first hypothesis test that we're going to be testing is for interaction. The null hypothesis is that there's no interaction. We always assume there's none. And then the alternative, if we reject the null, if our p-value is small for interaction, then we reject the null hypothesis that there's no interaction, and then we say, hey, there is some interaction here going on. Okay. And like I said, normally we would not, if we reject the null hypothesis that there's no interaction, then, and we say there is interaction between the two variables, then we would not interpret, we would stop right there. We would not interpret anything more further with the main effects. But if we fail to reject the null hypothesis and we think that there is no interaction between those two factors, then we would continue on and we would look at the main effects of factor A and the main effects of factor B. So we're going to have a p-value for factor A, and if the p-value is low, then we're going to reject the fact that there's no effect of factor A on the response variable, and we'll say there is an effect of factor A. Increasing A, either makes the response variable go up or makes the response variable go down. Or there's just, we'll know there is an effect. Okay, then the same thing with factor B. You're going to have a p-value for factor B. If the p-value is low, we're going to reject the fact that there's no effect on factor B, and we'll say there is an effect of factor B. It's working or somehow changing the response variable. So we're going to have 3 different p-values, and we'll always remember that there's no interaction, no effect are the null hypotheses here. And that kind of makes sense to me. We don't want to assume, sometimes, we don't want to assume a drug works or something like that. We want to prove the drug works. So we assume the opposite of what we're trying to prove. We assume that there is no effect, that the drug is ineffective. And then if the evidence supports the fact that it is effective, then we go ahead and make that conclusion. So, and factors might be a certain type of drug, right? And the same thing with interaction. We don't want to assume that there's interaction between two variables. So look at, to help you remember these hypotheses in this ANOVA test, there's no interaction in the null hypothesis here, no effect, and no effect in both of those factors. Okay, just to kind of help you remember these. Okay, so the next thing that we do I was already mentioning that. And they're just saying because the interaction clouds the interpretation of the main effects. Okay. And so just do, like I said, we check the interaction p-value first. And if the p-value is low for interaction, then we do not interpret the main effect hypotheses. Okay. All right. So here we go. Is a full example of 2A Anova. Recall the rice farmer who is interested in determining the effect of fertilizer on seed type on the fruiting period of rice. Assume that probability plots indicate that it is reasonable to assume that the data come from populations that are normally distributed. So they already took care of that. So we just have to verify the requirement, and they're probably also saying they're independent samples. And so we just want to verify the requirement of equal population variances. And we're going to use Minitab. We're going to enter all that data, or all of our data into Minitab, but they're going to give us all our p-values and we'll read it. And they make sure to say here, if there is no significant interaction, determine if there is a significant difference in the means for the 4 fertilizers and for the 2 seed types. So they calculate, they took the data from this page and they found the standard deviation of 13.5 and 13.9 in that cell. And then they went on to the next cell, 13.5 and 14.1, and then they found the standard deviation in each cell and they posted it here. They found the largest standard deviation, which is a 4.495, and they made sure that that is no more than twice the smallest. So twice the smallest is 2.283. If we double that, it's about 30, that's about 0.6, which 0.49 is no more than 0.6. So that is met. Next, we look at the output from, so they entered all of this data over here on this screen into their calculator in Minitab, and they get this calculator output. And so I won't be focused on you guys figuring out how to do it on the calculator so much. We're just gonna go through and make sure that when you see these outputs that you're able to read them and comprehend them. So first we look for the interaction. And notice, okay, so notice here that this is fertilizer interacting with seed right here. And our P is our P values. The P value there is large. And I believe 0.05 is the level of significance here. So this 0.46 is the P value for interaction. And it is larger than 0.0, the level of significance. So our P value is larger than alpha. So we failed to reject the null hypothesis, which was that there was no interaction. So we failed to reject the fact that there's no interaction. So we believe there is probably no interaction because we're not rejecting that. So there is no interaction, which means we can go further and we can now interpret both the seed and fertilizer. So now we focus on the p-value for fertilizer. The null hypothesis is that all 4 fertilizers have the same, basically the same effect on fruiting period. That was the null hypothesis. There's no effect of the factor fertilizer. And if the p-value is low, then we reject that. And we think that there is there is a difference in the different fertilizers and how they're affecting the fruiting period. So the p-value here is 0, so it is less than 0.05. So we reject the fact that there's no interaction due to fertilizer, and we say that one of these fertilizers is in fact working better than the others. Okay, and then we look at the p-value according to seed. That also is low because it's below 0.05. So there also is something going on when we change the seeds. The different seeds are also have different, statistically different fruiting periods as well. When we go from one seed to the other seed, they're significantly different. So that's our results here. Their effects from both seed and fertilizer, and there is no interaction between the two. So let's go on. And I put information here. If you use StatCrunch, you can also use a program called Minitab to do two-way Anova. The next thing I wanted to go over for you guys is to, you can draw interaction plots to see the actual interaction that's going on between the two variables. And so what you do is you compute the mean value of the response variable within each cell. And then you're going to label the horizontal axis each level of factor A, and the vertical axis will be the mean value of the response variable for each level of B. For each level of factor A, you plot the mean value for each level of factor B and draw lines to connect to the common levels of B. And you should have lines that are levels of factor B. The number of lines should be the number of levels of factor B. And the fact here is that the more difference there is in the slopes between the two lines, the stronger the evidence of interaction. And really, when they say difference between the slopes is one negative and one positive. Then that would be a significant difference. But if in general, if our lines are generally all positive, then there's not a huge there's not a lot of interaction going on. So here's an example. This is an experimental drug that's increasing HDL. It was meant to increase HDL cholesterol, and they have 3 different levels of the drug, and they have 2 different age factors. And so this is factor A over here, the age, the one that's the rows, and the one that's in the columns is factor B. So what they do is they put factor A, the different levels of factor A, along the X horizontal axis. And then for each factor of B, we're going to have 3 different lines to express that, to see that. And so they take the mean of this, the mean value for these, the mean value for these, the mean value for these, and so on, the mean value for those, the mean value of these, and the mean value of these. Okay, and then they're going to draw one dot on the graph to represent this, draw a dot for that, and then they're going to connect the dots for each level. And so we're going to end up having 3 lines. And so you're going to see whether, if you're going to see in a minute, like when we go from low to high, does it increase or decrease? But it should, if there's no interaction, then they should all be decreasing, or for every level of for every level of drug dosage, the same, either increase, decrease, or decrease for every instance of going from low to high of factor A. So let's see what it looks like. But I did the dot here, but actually we're going to be plotting it on the Cartesian coordinate, but just that's a little bit, just overview of what we're doing there. A simplified version of what we're doing. So they find the mean, just like I said, in every cell. And so then they took the, like I said, they took the factor A and put the low level and high level. And then they also did, for the first level of B, they did the 2 and the 1.7. And so then they connected the dots that were the same level of B, and they've labeled it placebo. And then they did the 6.7 and 5.3, and then they labeled those 5 milligrams of placebo, 5 milligrams, and then they connected them because they're the same level of B. And then the same thing with the last one, they did the 12 and they did the 8.3, and they connected them because they were both the same level of B. And this is their interaction plot. And notice how, what I notice is as I go from 18 years to 40 years old, that is, as I change see a change in factor A, factor B goes slightly down. Factor A goes down slightly when I go from high to low, right? How it's going downward. And so it's still like a decreasing slope when we go from between the different age categories. So there does not look like there's any interaction. They all are decreasing. So let's look at some graphs of, so this is how you would do your interaction plot, but let's look at what it would look like if there was interaction going on. So if they in general have the same kind of curve, increase between these two and decrease between those two, then there's no interaction. If they kind of have the same increasing over the same interval, there's an interaction going on. This second one, where notice that the response variable, when you increase A here, at a low level of B, or whatever B1 means, then the response variable increases a lot. But you changed B for B3, maybe we increased it, and now the response variable is decreasing as we increase the level of A. So that means that there was a significant difference when we changed B. Now, all we did, we're just changing, when we go from left to right here in the picture, all we're doing is changing the level of A. And we would expect the same change for all 3 levels of B if there was no interaction going on. But here, the response variable, when you change B to B, from B1 to B3, all of a sudden it looks like the drug is not working, or it's something happened. The response variable went way down for instead of, when we increase from A1 to A3, the B1 is increasing. The response variable increased for B1. But when we go from A to 3, then, and we change the level of B, then all of a sudden the response variable is doing the opposite, going down now. So this is definitely a significant interaction. And you can just, to summarize it, the slopes are very different, literally going from positive in B1 to negative, decreasing in B3, right? Okay, then here's some interaction. This is what the picture would look like. So like, they all kind of look like, this one kind of looks like, you know, it's increasing, then increasing more quickly. And this one's kind of flat. Those are kind of both flat and kind of both increasing. But there is sort of a crossing of the lines here. it kind of sort of looked like B1 worked a little bit better, because the response variable was higher for the first treatment of B1, a low level of B, and a high, so it looks like a low level of B and a high level of A are working really well. Look at that, it's high. But then if you have a higher level of B and the same level of A, it's a little lower than just a lower level of B, which is kind of, that is, so something's going on there. So since these lines cross, there's something going on there. And then this is called significant interaction as well, like just because I said, because some lines, are basically, it's saying as you increase A, the response variable, when you have B at a low level, it's going down. The response variable is going down. But then you have a high level of B and the complete opposite happens. That when you increase A, the response variable is going up. So if the response variable is like weight gain, and at a low level of B, A is working and causing you to lose weight. But at a high level of B, A is not working, it's causing you to gain weight. So, and then at a medium level of B, it looks really weird that like, actually it's not helping you gain weight or lose weight at all, because the response variable is just staying the same over as you change A. So there's significant interaction because you have positive slopes and negative slopes and zero slopes. Significant interaction because the same thing, we have zero, negative, and positive slopes. A little bit because they do cross just a tiny bit. And if the slopes are generally all the same, then there's no interaction. So that's the interaction. All right. So let's go on, moving from there. And here's some StatCrunch. It's a statistical program that can help you do this 2A Anova. Last but not least, we're going to look at how, now once we're done with the 2A Anova test, and we say, hey, there is an effect from factor B, or there is an effect from factor A, then we perform Tukey's test to actually figure out more about what's going on and which fertilizer is working and higher than the others, and which ones are smaller. So once we reject the equal hypotheses population for either factor, we proceed to Tukey's test. And I'm not going to have you be doing this by hand, but there's some important information if you were doing it by hand. So they just do this using Minitab at a level of significance, or what they call family-wise error rate. They call it a level of significance family-wise error rate here at 0.05 for the Tukey's test. And there's two ways of doing this Tukey's test, and there's a confidence interval method. And so it's very similar to Tukey's test that we did in the previous section. See, they compare fertilizer 1 was subtracted from fertilizer 2. So then they do a confidence interval for this difference, the difference between the two of them, and they say that they are 95% confident that the difference between fertilizer 1 in the difference in the fruiting period between fertilizer 1 and fertilizer 2 is between 1.1 and negative 6.9. So see these numbers here, the upper and lower. And the big thing is here is it does contain 0. So they think there's really no difference between fertilizer 1 and fertilizer 2. So we could say the mean of fertilizer 1 is equal to the mean of fertilizer 2. And that's because we look at this interval and this 0 on the number line falls inside that interval. Okay, so we say the means are equal because we're 95% confident that the difference is somewhere close to 0. Okay, then we look at between fertilizer 1 and we're comparing it to fertilizer 3 in this line right here and in this interval. in this interval, it does not contain 0, right? 0 is right here, so 0 does not fall inside of these parentheses. So we think there is a difference, that the mean of 1 for the mean fruiting period for fertilizer 1 is not the same as 3. So that means one of them is larger. And actually we can see they subtracted 1 from 3. So they did, when they did these calculations, 3 from 1. And they said that that was, and we look closer at this interval, it's above 0. And the lower bound is listed here as 0.1 and the upper bound 1.9. So that's all positive. So that means that if they did this calculation, mean of fertilizer 3 minus mean of fertilizer 1, they got it positive. We're 95% sure that that difference is positive. That means the fertilizer from 3 had the mean fruiting period was larger for fertilizer 3 than fertilizer 1. Then when we look at the last one, from 1 and 4, they're comparing 4. It does not include 0, because 0 is over here, right? And that's not included in these parentheses. So that we are convinced that the mean of 4 is not equal to mean of 1. So they're subtracting 1. They did the mean of 4 minus the mean of 1. And they're saying it's positive. It's really big positive, actually. So they're saying the mean of 4 is larger than the mean of 1. Now they compare fertilizer 2 to 3 and 4, because they already compared 2 to 1 up here. So 2 to 3, they took the mean of 3 and 2 subtracted from 3. So that means 2 is taken away from 3, and they got this interval, and it does barely contain 0 right here, right? So we think that mean of 3 is equal to mean of 2. Then they compare 2 to 4, and we look at this interval over here, and it does not contain 0, so we think that they're different. The mean of 2 is different than mean of 4. And not only do we think they're different, but it's a positive difference. And the calculation we did was 4 minus 2. So we think that 4 is larger than 2. Because this interval is strictly positive numbers. We're 95% confident that the difference between those two means is a positive number, which would mean that the larger, the one we were subtracting from was the larger one. So then the last comparison that we do here is is between mean 3 and mean 4, and it does not contain 0, which is right here. So we think that they're actually different. And they subtracted 3 from 4, so the mean of 4 minus the mean of 3, and that would give us a positive answer. So we think 4 is larger than 3. All right, and so they sum up everything on the next page, I believe. They say, yeah, and they just say everything that I just said, and they sum it all up, and they more summing it all up. They also may show you the p-value approach to this Tukey's test as well. And instead of looking at confidence intervals and looking at whether 0 is in the confidence interval or not, this one looks at a p-value. This one isn't as good because the other, with confidence intervals, it tells you whether it's even negative or positive. What is the difference, possible difference, and what is, if it's negative or positive, which mean was larger. Here, this one just gives us a p-value, so all we know is that they are different. So first of all, 1 is compared to 2, that p-value is large. So we do not reject the fact that they were equal, so we conclude that they are equal. Then we compare 1 to 3, the p-value there is low. It's less than 0.05. So we conclude that the mu of 1, the mean of 1 is not equal to the mean of 3. And then the same thing for 1 versus 4, the p-value is low, so we reject the null hypothesis that the means are equal, so we say that the means are not equal. Then we compare 2 to 3, the p-value is large, so we fail to reject the null hypothesis. And we say that the mean of 2 is probably equal to the mean of 3. And we compare 2 to 3, and that is 2 to 3, and the 2 to 4, I'm sorry, and the p-value is lower than 0.05. So then we think the means are different. And then last but not least, we could use 3 to 4, the p-value is low, below 0.05, so we say those means are also different. So if the p-value is low, we say the means are different. If the p-value is high, we say the means are the same, right? And that is how we would, and here is it all summed up in words for you if you missed any of that. And that's how we interpret the results to the two-way Anova test and full Tukey's test as well. All right, so I hope that you found this very valuable, and please email me if you have any questions. Bye.